Hey, Assalamualaikum. Good morning, everyone. I am now on my lecture 6 for CHM477, which is inorganic chemistry. The topic that I'm going to be discussing today is the next topic in our schedule, which is the molecular orbital model or delocalized electron model. We have finished discussing the valence bond theory, the localized electron model. So the localized electron model consists of the Lewis model, the Lewis structure, valence bond theory, and hybridization. Now these three in combination, they are of great value to interpret the structure and bonding of molecules. However, there are some weaknesses to this model, in which that the model or the localized electron model still does not address the energy aspect and cannot explain some of the experimental observations made on certain molecules. Now, the problems that are encountered with the localized electron model are many, but three of them are here. The first one, there is no direct information on the bond energies. All you know is that it has how many lone pairs of electrons, how many bonding pairs of electrons, what is the geometrical shape, and what is the hybridization um, that is attached to that geometry. There is no information on the energy of bonds in that molecule. Number two, it assumes that all electrons are localized. Localized means that they stay in one place. That means they do not move. But that is not correct. We all know that electrons move. They do not stay put in one place. Therefore, with that, the concept of resonance had to be added. So that was what I covered in one of my lectures previously. And number three, the localized electron model does not deal effectively with molecules containing unpaired electrons. Now, be very careful to distinguish between lone pair of electrons and unpaired electrons. Lone pair of electrons are two electrons that are not being used in bonding. They are present, but they are not being used in bonding. Those are lone pairs of electrons. But unpaired electron is one single electron that does not have a pair. It exists only one in one orbital, so we call it unpaired electrons, i.e. it cannot explain the paramagnetic properties of molecules such as oxygen. Now, it has been shown experimentally that oxygen molecules are paramagnetic. How is that? How is that established? When liquid oxygen is poured into the space between the poles of a strong magnet, when you cool down oxygen sufficiently enough until it reach the boiling point, that means it changed from gas into liquid, you're going to get liquid, obviously. And when you pour that liquid between the space of the poles of strong magnet, between the north and the south poles of a magnet, that means there is a magnetic field between the two poles. What was observed is that it remains there until it boils away. That means the oxygen is very much attracted to magnetic field. It will stay where the electromagnetic field is. This attraction of liquid oxygen for magnetic field demonstrates the paramagnetism of oxygen molecule. Now you may not understand what is paramagnetism, so I give you an additional note here which you do not have in your original note that I gave you. Paramagnetic compounds contain unpaired electrons. They are attracted to applied magnetic field. I missed a 2 here. Applied magnetic field. Yep, that's it. Yep. Attracted to applied magnetic field. That is paramagnetic compound. The other type of magnetism is called diamagnetic. Now, diamagnetic compounds contain only paired electron. That means all the electrons in diamagnetic compounds are nicely paired up. If you have one spin going that way, there will be another electron going on the other opposite direction. So you have the electrons nicely paired up. And diamagnetic compounds are repelled by applied magnetic field. Repelled means it's not, if oxygen was diamagnetic, it would not stay here between the poles of these two magnets. It will not stay here. It will be pushed out of the magnetic field between these poles of magnet. So what was observed was that pouring liquid oxygen between north and south poles of a magnet, what you see or what our scientists see was that that oxygen liquid stays nicely between the two, and then until it boils away, until it becomes too warm, it becomes gaseous. So that shows that oxygen is paramagnetic. However, when you draw a Lewis diagram of oxygen, you will find that you have a double bond between the two oxygen. You are an expert at this already. You have lone pairs of electrons on the oxygen on the left. You have two lone pairs of electrons on the oxygen on the right. There are no unpaired electrons. All electrons in oxygen are paired up, and it is expected to be diamagnetic according to this picture. However, this diamagnetism is not reflected in the experiment that was carried out here. Yeah. To overcome the problems stated, the problems 1, 2, 3 here, the molecular orbital model is introduced. Yeah, molecular orbital model is introduced. So the localized electron model doesn't work very well to explain magnetism. It doesn't work very well to explain colors and so on. It doesn't give you any kind of energy information. So molecular orbital model is introduced, and this molecular orbital model is also called delocalized electron model. Delocalized means that it doesn't stay in one place. To understand the assumptions, methods, and results of this model, we will consider the simplest of all molecules, which is hydrogen. Hydrogen is the simplest molecule because you only have one electron in one atom combining with another electron in another atom to make a molecule which has a single covalent bond between it. Now, when this is just another quick recap, when you have two non-metals combining to make a molecule, then that molecule is covalent. But when you have a non-metal with a metal combining to make a compound, so that compound is ionic. So ionic compound is made up of metal and non-metal, whereas covalent compounds are made up of non-metals. Okay. Now, to understand the assumption, methods, and results of this model, we will consider the simplest of molecule, which is hydrogen, which consists of two protons and two electrons. Yes, one proton, one electron from one hydrogen, another proton, and another electron from another hydrogen. Now, H2 is a very stable molecule, and the molecule is lower in energy than the separated hydrogen atoms by 400, and I missed an S there, by 432 kilojoule per mole. Now, molecular orbital theory states that bonds are formed from the interaction of atomic orbitals that makes molecular orbitals. So when atomic orbitals combine, they make molecular orbitals, and that is when bonds are formed. The atomic orbitals have to overlap so as to concentrate electron density between the atomic cores, or between the two nucleus of the atoms. The criterion of net positive overlap of atomic orbitals can be used as an indication whether the bonding will occur or not. Yeah, let's just follow this lecture through. So the central theme of molecular orbital theory is that a molecule is viewed on a quantum mechanical level. All these are solved mathematically. Yeah, all these models originated from mathematical models. Quantum mechanical level as a collection of nuclei surrounded by delocalized molecular orbitals. I'm going to explain this to you later. Atomic wave functions are summed to obtain molecular wave function. If wave functions reinforce one another, a bonding MO or molecular orbital is formed where there is a region of high electron density that exists between the nuclei. And if the wave functions cancel each other, an anti-bonding molecular orbital is formed where there is a node of zero electron density. Apa pula zakirangan tahu pada saya ni? Nanti saya semak. A node of zero electron density occurs between the nuclei. You may not understand this, but you will understand it as we go along. And the person who came up with all this mathematical equation and come up with the model is called Schrödinger. Schrödinger, yeah? He's a European scientist. Schrodinger's equation, I'm not going to go through this. This is too detailed for you to understand. If you are interested, I have handouts that I can give to you. Now, I was saying that when you are expecting to have a bond to form between two atoms, that means the orbitals of those atoms must overlap. Remember what are the atoms in what are the orbitals in an atom? Remember the S, the P, the D, yeah? The S, P, and D orbitals. Those orbitals will overlap when the two atoms approach one another. And the overlap of these orbitals can be described like this. When two atoms approach each other closely enough for the orbital on one atom to overlap with the orbital of another atom, three types of overlap may occur. You can have a positive overlap, you can have a negative overlap, and you can have a zero overlap. So what are those overlaps? Okay, let me go through the positive overlap with you first. Now, when the superimposed regions of the two orbitals have the same sign, either both positive or both negative, the results of the positive overlap is a strong attractive force of bonding interaction and a higher electron density for the molecular orbital than the sum of the two separate orbitals. So you get bonding molecular orbital upon positive overlap. An example is this. Now, this is one s orbital. This is another s orbital. When they overlap, now s orbitals will only have one sign. It can either be all positive or all negative, unlike p. This is p orbital. It has two lobes. If you can recall the dumbbell shape of a p orbital, so the two lobes will be one positively not charged, positively marked or positive sign, and another is a negative sign. So, but s orbitals are all the way through the s orbital, it is a same charge. So I'm going to just use plus here. You may have a minus as well. So when two s orbitals overlap, they will have the same charges or the same signs overlapping, so they will reinforce one another. Yeah, they will reinforce one another, and you are going to have a concentration of electron density between these two nuclei. This is one nucleus of one atom. This is another nucleus of another atom. You have the two atoms overlapping. You're going to get a positive overlap because the signs are the same. This is another example of a positive overlap between the s orbital and a px orbital. Yeah, px orbital on the x-axis. The positive sign overlap with the positive lobe of the P, so this overlap will make a positive overlap, and you're going to have a concentration of electrons happening between this nucleus and that nucleus. Yep, and this will become small. This will become small. So this is SP. You recall? Can you recall hybridization story now? SP. Now here is another example of a positive overlap. This is a d orbital. It can be dx, y, yeah, dxy, and this is the xz, and this is your pz. So pz is on the z-axis, so you have the positive signs overlapping together, the negative signs overlapping together, and so this is a positive overlap. And this is another example where you have your py of one atom overlapping with the py of another atom. So you have the positive overlap of the positive signs and the negative signs together. So this will make a positive overlap of pi nature. This is also pi because it's side to side. Here is head to head, so you get a sigma bond here. Here also you get a sigma bond. In here you get a pi bond. In there you get a pi bond. So those are 4 examples of positive overlap. Now the second type of overlap is negative overlap. Negative overlap is when the superimposed region or the overlapping region of the two orbitals have the opposite signs, positive and negative overlap. So you have a negative overlap. The result is a reduced shared electron density and increased internuclear repulsion. So you get an anti-bonding molecular orbital. If at the top here you get bonding molecular orbital, at the bottom you're going to get anti-bonding molecular orbital. So this is one example. If you overlap px of one atom with px of another atom, but they have the opposite signs overlapping, that means this minus that, yeah? So you are going to have an antibonding happening because this is a negative, this is a positive sign. So you're going to have a reduction of electron density between the nuclei, but an increased electron density outside of the nuclei. Yep. This is another example of a negative overlap, which is a negatively charged s orbital with a positive lobe of a px. This is also negatively charged. A negative overlap. This is also negative overlap. That is also negative overlap. Yeah, so a negative overlap will give you antibonding molecular orbital. And a zero overlap is when the overlap is not effective. You have, for example, this is one example of a zero overlap. When there are precisely equal region of overlap with opposite sign. Here you have a negative with positive, but down here you have a positive with positive. So the effect of this positive overlap is offset by the effect of this negative overlap, so you get a zero overlap. Similarly in this picture, similarly in that picture and this picture. That in here you have no overlap at all because they are, one is on the z-axis, another is on the y-axis. There is no possibility that these two orbitals will overlap. So we call that zero overlap, and the interaction is called a non-bonding interaction. So remember, you have a bonding interaction for positive overlap, you have an anti-bonding interaction for a negative overlap, and a non-bonding interaction for a zero overlap. So those are the three overlaps. Remember this because we are going to go into it later when we talk about the combination of the atoms. Now, here I'm going to go direct into the LCAO, which is a linear combination of atomic orbitals. So that means the atomic orbitals are combined linearly. In simple words, is either you add them together or you subtract one from another. Just a simple linear combination. Now, linear combination is an approximation and simplification which supposes that we can construct molecular orbitals from linear superposition or overlap of atomic orbitals centered on individual atoms. So this is probably a handful, but just read it slowly, you will understand it. But I don't know your background of chemistry, whether you have learned about electron configurations or not. But I think before I go further into LCAO, I need to do a quick revision of the Aufbau Principle and the building of a periodic table and how to write electron configuration of atoms correctly. So let's go straight to the handout that I have just sent to you through Google Classroom, which is the electron configuration handout, additional notes number 2. So I have additional notes number 2 at the end of this. I can go straight there. Right. Second. There you go. So I'm going to do a quick revision on the Aufbau Principle, the building of the periodic table, and electron configuration of atoms. And all these materials are taken from the textbook by Zumdahl, Steven Zumdahl. Now, what is the Aufbau Principle? I'm sure you have heard of Aufbau Principle. It says that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the orbitals. This is called Aufbau Principle. Now, for example, we start with hydrogen. Hydrogen has one electron, which occupies the first orbital, which is the 1s orbital in its ground state. The configuration of hydrogen is written as 1s1. So if you remember in the first series of periodic table, I'll show you here. This is your first series. Hydrogen and helium are the only two elements in the first series. So hydrogen, it only has one atomic orbital, which is the 1s orbital. So the 1s orbital here for hydrogen is filled singly with one electron, of the hydrogen. So this is 1s1. As you move along to helium, the second electron comes in and it pairs itself up with the first electron in here. So it becomes 1s2. It cannot go to the 2s because 2s is not accessible for the helium because helium happens to be in the second series, the first series. The second series, you have 2s and 2p orbitals. In the first series, you have only one s orbital. Now, so helium, the electron configuration of helium is 1s2. When we move on to lithium, here is your lithium, adding one more proton. Remember Aufbau Principle, adding one proton into the nucleus of an atom, you have to also add one electron because the proton has a positive charge and it has to be neutralized by the negative charge of the electron. So adding one more proton into helium will give you lithium. And adding one proton to make lithium means you have to add one electron on the next available orbital, which is the 2s orbital. You cannot put another electron in here because each orbital can only accommodate a maximum number of 2 electrons. So the third electron has to go into the 2s orbital. So that is lithium. So lithium is 1s2, 2s1. So that's quite simple. So going on to beryllium, adding one more electron into here, beryllium cannot go and put one electron there because this is of a higher energy. P orbital is higher energy than the s orbital. Remember, I went through that with you in the beginning of the lecture. The energy level of the s and the p, yeah, s orbital of the same series has lower energy level than the p orbital, and the d orbital will have the higher energy level than the s and the p. Because the p orbital is at the higher energy level, when you add one more electron to make beryllium, the fourth electron will go in and pair up with the third electron in the 2s orbital. So beryllium will be 1s2, 2s2. Yep, there you are. 1s2, 2s2. Very nicely summarized in this picture. This is the first, second, and third series of your periodic table. So you have 1s2, 2s2 for beryllium. Adding one more electron makes you have to add the fifth electron on the p orbital here. For boron, the fifth electron will have to go into the p. So you have 1s2, 2s2, 2p1. So you get the idea? Carbon electron will be the sixth electron will go into this. If this is px, this is py, that is pz. So it will occupy py singly. Now there is another rule which is called the Hans rule. It says that the Hans rule saying that the lowest energy configuration is the one having maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbital. Degenerate orbital means orbital of the same energy level. So when you have orbitals of the same energy level as the p here, so you have your 2px, 2py, 2pz. When the next electron come along, it cannot go and pair up with this. It has to occupy this singly first. So you have here for carbon 1s2, there you are, 2s2, 2s2, and 2p2, 2p2, 1s2, 2s2, 2p2. The next one is nitrogen, again following the same Hans rule. It cannot pair up until all the orbitals of the same energy level is filled. So it will fill up the 2pz orbital here. So you have 1s2, 2s2, 2p3. Yeah, 1s2, 2s2, 2p3 for nitrogen. Moving along to oxygen, the electron number 7, what am I? Electron number 8 will have to start pairing up. It will have to start pairing up. It cannot make any more unpaired electron. It has to start pairing up because there's no more empty orbital. So you have 1s2, 2s2, 2p4 for oxygen. And for fluorine, 1s2, 2s2, 2p5. And for neon, 1s2, 2s2, 2p6. When you reach neon, the orbitals on n equal 1, that means the first series, this is your n equal 1, the 1s, and n equals 2, these are your second series where you have the 2s and the 2p, they are all completely filled. So neon is a very, very happy and stable element, it will not react because it has filled up all the electrons in its orbital. Yep. So with neon, the orbital with n equals 1, series 1, n equals 2, series 2 are now completely filled. The next element, oh, there you go. The next element after neon is sodium. Na is natrium, as you know it, but in English we call it sodium. No natrium, please. We are using the word sodium from now on. So the electron number, this is what, how many? 8, 10. Electron number 11, atomic number 11. The next electron will have to start going into the third shell. Yep. You have 3s1. And then the next one will be 3s2. Your magnesium is 3s2. So when you have a very, very long electron configuration like this, 1s2, 2s2, 2p6, 3s1, there is an abbreviation that you can use where this 1s1, 1s2, 2s2, 2p6 can be abbreviated as a neon in the square bracket. So it is easy for you to say it's neon 3s1. So neon 3s1 is sodium, neon 3s2 is magnesium, neon 3s3 is, what is neon 3s3? It is aluminium. Silicon is neon 3s4. No, I'm wrong. There is no 3s3. Aluminium is neon 3s2, 3p1. Yep, 3p1. Whereas silicon is neon 3s2, 3p2, phosphorus neon 3s2, 3p3, 3p4, 3p5, and argon is neon 3s2, 3p6. Yep, coming on to argon. What is your argon here? Coming up to argon, you completed one more series, and so on and so forth. So I hope you now understand how electron configuration for atoms are written, because this knowledge is going to be useful when we start to talk about molecular orbital. We are now still talking about atomic orbital. When we deal with molecular orbital, it is the same principle that we adopt. Okay, going back, this is a quick revision. Going back to overlap. Going back to overlap here. Oopsie. Okay, going back to overlap. Oh, excuse me, I'm making me dizzy. I am making myself dizzy. That's it. Dizzy. Right. Going back to LCAO. Linear combination of atomic orbital. Now, molecular orbitals have very much similarities with atomic orbitals. Two of the most important similarities are one molecular orbital can hold only 2 electrons of the opposite sign. When you have the spin up, we call it positively signed electrons. Bukan positively charged, it is the electron with the positive sign. And then the electron that has a different direction spin, we call it negative sign. So it has the opposite spin, the positive spin and the negative spin, because electrons spin. Yeah. Number 2, the similarities between atomic orbital and molecular orbital is the square of the molecular orbital wave function indicates the probability of finding electrons in that specific area. And this is mathematical. Now, taking 2 hydrogen atoms, each having 1 electron in their 1s atomic orbital, when the quantum mechanical equation for the hydrogen molecules are solved, 2 molecular orbitals will be obtained. Okay, pay attention. This is a picture. I'm going to make it slightly smaller so it can be seen clearly in the label here. This is the energy level diagram for bonding and antibonding molecular orbital of hydrogen atom. Okay, this is the atomic orbital of one hydrogen atom. This is the atomic orbital of another hydrogen atoms. When they approach one another, there will be a positive overlap and a negative overlap. A positive overlap will give you bonding molecular orbital, which is a sigma bond. Remember this picture? Yep. This is a positive overlap of a atomic orbital producing bonding. Yep. And there is a negative overlap where you have antibonding molecular orbital. We call this sigma 1s. Sigma because the overlap is head to head, not side to side. So sigma bonding is a result of the head-to-head overlap. And we call it sigma 1s because this is obtained through the overlap of 1s orbitals. Positive overlap of a 1s orbital. Whereas this one is a negative overlap. This one is when you add the two together mathematically. This plus this gives you that. Whereas this minus that will give you this antibonding molecular orbital through the negative overlap, and we call it sigma asterisk 1s or sigma antibonding 1s. So the picture of this formation is two s orbitals overlapping positively, constructive interaction to make your sigma bond, which has a shape like this. The electron density between the two nuclei are increased. Here you see there is small amounts of electrons between the two nuclei, but here as a result of the constructive interaction, you have an enhanced electron density between the two nuclei. So that is constructive, or you have a plus interaction. At the top here, you have a destructive interaction, whereas this minus that. So destructive interaction will produce antibonding sigma molecular orbital. Is still a sigma bond, but it is a negative overlap, and it will make a sigma antibonding 1s, and the shape of electron density is like this. It looks like a Pumbaa, if you can recall your Lion King. Do you recall Lion King? You have that warthog Pumbaa. This is like the eye of Pumbaa, and this is the nose of Pumbaa. So you have the electron density between the nuclei becomes less, but the electron density outside of the nuclei this way becomes more and more. So it has fatter on that side, thinner on the inside. Whereas opposite is true for your bonding molecular orbital. So your bonding molecular orbital has this shape, antibonding molecular orbital has that shape. So that is the first picture. Now, a bonding molecular orbital has lower energy and greater stability than the atomic orbital from which it is formed, and an antibonding molecular orbital has higher energy. Remember, higher energy. Highlight that. Put myself somewhere else. Yep, higher energy. This one has lower energy. Yep. When you have a bonding molecular orbital, this has a lower energy. Oops, there you go. Yep. This is your original atomic orbital energy level. On this level, the bonding will have a lower energy level, whereas the antibonding will have a higher energy level. Higher energy level means it is less stable. Lower energy level means it is more stable. So this is the picture of constructive interference when you have wave 1 and wave 2 are adding on phase. You have this phase enhancing the other phase. It will make a higher peak here. This and added to that will make, this is you learn in physics. You have a constructive interference where enhancement of electron density happens between the two nuclei, whereas when you have destructive interference is when this positive is meeting the negative becomes 0 and the negative is meeting the positive becomes 0. Sum of this will become a antibonding molecular orbital or destructive interference. Yeah, so that is the origin of bonding molecular orbital sigma 1s and antibonding molecular orbital sigma antibonding 1s for your hydrogen atom. So I think for now I'm just going to leave it there because I would like you to digest the information, and I'm going to make another video which will be going deeper into this LCAO, linear combination of atomic orbital, that involves p orbitals. For now, we only have s orbitals in our consideration. So until then, I hope you can understand this lecture and you can take this understanding into my next lecture, which is a little bit deeper than what this is. So thank you. See you later. Have a good day. Bye.